Tunisia, April 1943. In the pre-dawn darkness outside the town of Mateur, a sound echoed across the valley that made German forward observers instinctively reach for their field glasses. It wasn't the rumble of advancing armor or the crack of artillery. It was something more unsettling, the constant, throaty idle of dozens of American tank engines, running hot through the night, wasting fuel that by all logic of desert warfare should have been carefully conserved. Obergefreiter Kurt Schneider of the Fifth Panzer Army pressed his binoculars against his face, scanning the Allied positions 2 kilometers away in the grey morning light. What he saw defied every principle of armoured warfare he'd been taught. American M4 Sherman tanks, lined up in tactical formation, their engines running continuously, exhaust shimmering in waves above their engine decks. They'd been idling like that for hours, perhaps all night. The fuel consumption alone would have been unthinkable for a German unit. Schneider turned to his commander, Lieutenant Richter, confusion evident in his voice. "Sir, they're still running their engines. All of them. They've been doing it since we took position at 2200 hours. Richter didn't lower his own binoculars, his jaw tight. "I know. I've been watching." If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The silence between them carried the weight of understanding what this simple observation meant. It meant the Americans had so much fuel, so many spare engines, so many replacement parts, that they could afford to waste them. It meant Germany had already lost the mathematics of war, even if the shooting continued. To understand why American tank crews deliberately overheated their engines and ran them far beyond what German doctrine would allow, you need to understand what they'd been told about their own equipment. The M4 Sherman tank, which would become the workhorse of American armoured forces, arrived in North Africa with a mixed reputation. Its armour was adequate, but not exceptional. Its 75mm gun was effective but less powerful than the German 88. Its speed was decent but not remarkable. By every metric of individual combat performance, it appeared inferior to German armour. American tank crews arriving in North Africa in late 1942 and early 1943 knew this. They'd heard stories about Tiger tanks and Panthers. They'd been briefed on the fearsome 88mm anti-tank gun. Some had witnessed firsthand at Kasserine Pass how German armour could devastate inexperienced American units. The narrative seemed clear. American tanks were outclassed in direct combat. But what the tankers discovered in the brutal conditions of the North African desert was something their training hadn't emphasized. The Sherman had one overwhelming advantage that changed everything. It was reliable, absurdly, wastefully, impossibly reliable by the standards of any other army in World War II. And this reliability created a tactical doctrine that would have been considered reckless insanity to German or British commanders. The deliberate overheating of engines. The practice started informally among veteran crews who'd survived the initial disasters of Kasserine. Sergeant Mike Kowalski of the 1st Armored Division, a tank commander from Detroit who'd worked in automotive plants before the war, noticed something during the chaotic retreat. While American tanks broke down, they broke down predictably and could be repaired quickly. More importantly, when they didn't break down, they kept running under conditions that would destroy other engines. After Kasserine, as American forces regrouped and prepared for the final push to drive Axis forces from Africa, Kowalski began experimenting. Instead of shutting down his Sherman's Continental R975 engine during defensive positions, as doctrine suggested to conserve fuel, he kept it running, not at full throttle, but at a steady idle that kept the engine hot and ready. The oil stayed fluid, the coolant circulated, and most crucially, the tank could move from stationary to combat speed in seconds, instead of the minutes required for a cold start. His crew thought he was crazy. "Sarge, we're burning fuel for nothing," his driver protested after the first night of continuous idling. "We'll run the engine bearings hot. We'll burn out the seals." Kowalski, leaning against the turret with a cigarette, just smiled. "Kid, when's the last time supply told us we were short on fuel?" The driver opened his mouth to respond, then closed it. The answer was never. Not once since arriving in North Africa had American units faced genuine fuel shortages, unlike the Germans who were constantly scrambling for petroleum. The tactical advantages became apparent during the next engagement near Sidi Bouzid. When German tanks appeared on the horizon, Kowalski's platoon was ready instantly, while other tanks, both American and British, needed precious minutes to start cold engines, check systems, and begin moving. Kowalski's Sherman was already advancing, gun traversing, and crew coordinated. Those extra minutes meant his tank reached effective firing position first. It meant he chose the engagement range, not the enemy. Word spread fast among American armored units. Tankers started keeping their engines running during static positions, during brief halts, during night defensive perimeters. They idled their Shermans continuously, letting the Continental radial engines purr through the desert nights, consuming fuel at a rate that would have court-martialed a German commander for criminal waste of resources. But for Americans, it wasn't waste. It was doctrine built on the bedrock foundation of overwhelming material superiority. The Sherman's Continental R975 air-cooled radial engine was designed with massive tolerances precisely for this kind of abuse. It produced 350 horsepower at 2,400 RPM, but its real strength wasn't power output. It was the engineering philosophy behind it. Every component was overbuilt, every tolerance generous, every part designed for replacement rather than precision maintenance. The engine could run hot, far hotter than German engines, because American metallurgy and manufacturing could produce parts that withstood thermal stress. The cylinder heads were cast with extra material to handle expansion. The valve seats were hardened beyond what precision would demand. The oil system was designed with extra capacity and additional filtration because American logistics could supply oil in quantities other armies couldn't imagine. Staff Sergeant James Butler, a tank mechanic with the 2nd Armored Division, kept detailed notes in his personal diary that survive today in the National Archives. His entry from March 1943 reads, "Examined engine from Lieutenant Dawson's tank after continuous operation for 72 hours, including combat. Expected major bearing wear. Found minimal degradation. Oil pressure steady. Cylinder compression within specs. This engine is designed to be abused." That's the only explanation. Butler's observation captured something profound about American military-industrial philosophy. German tanks were precision instruments, engineered to extract maximum performance from carefully measured resources. They required skilled mechanics, specialized tools, and gentle operation to maintain peak efficiency. A panzer crew that ran their engine unnecessarily would face discipline for wasting precious fuel and reducing engine life. American tanks were industrial tools, designed for soldiers who might have been farmers or factory workers months earlier, built to withstand abuse, because the factories back home could simply build more. The Sherman wasn't engineered for elegance. It was engineered for mass production and battlefield reality, where soldiers under fire don't have time for careful maintenance procedures. The contrast became visceral to German tankers as the North African campaign progressed toward its inevitable conclusion. Lieutenant Richter, the officer who'd watched American tanks idling through the night, commanded a Panzer Mark IV, a capable tank by any standard. But his crew lived under constant constraints that American tankers couldn't comprehend. Fuel was rationed with the arithmetic precision of desperation. Each mission required careful calculation of distance, terrain, and expected engagement time. Running the engine unnecessarily, even for 5 minutes, meant potentially not having enough fuel to reach the next position or execute a tactical retreat. The Maybach HL-120 engine in Richter's Panzer was powerful and sophisticated, producing 300 horsepower from 12 cylinders of precision German engineering. But it was also temperamental, requiring specific maintenance intervals, particular grades of oil, and gentle warm-up procedures. German tank doctrine emphasized cold starts to conserve resources. Crews would wait until the last possible moment to start engines, then carefully warm them through a graduated procedure that could take 5 to 10 minutes before the tank was ready for combat maneuvering. In static defensive positions, Engines were shut down completely to save fuel and reduce thermal signatures that Allied aircraft might detect. This created a tactical vulnerability that American tankers, keeping their engines hot and ready, exploited ruthlessly. When contact occurred, American tanks were already moving while German crews were still going through startup procedures. Those extra minutes translated into position, into choosing engagement range, into living or dying. British tank crews, operating their own Shermans through Lend-Lease as well as their domestic Crusaders and Cromwells, noticed the American practice with a mixture of admiration and concern. Captain Nigel Worth of the 7th Armoured Division wrote in a letter home dated April 8, 1943, "The Yanks run their tanks like taxicabs with the motor always running. Our own doctrine would call it wasteful, but I've started doing the same. We have the fuel, we have the parts, and we have tanks that won't quit even when we ask them to work harder than any reasonable engineering would allow." The overheating wasn't just about keeping engines running. American tank crews pushed their Shermans harder in combat than doctrine suggested, accepting higher operating temperatures because they knew replacement engines existed in massive supply depots. They climbed steeper grades in higher gears, knowing that even if they burned out a transmission, another would arrive within days. They forded water obstacles without elaborate waterproofing procedures because damaged electrical systems could be swapped quickly. This aggressive operational tempo, enabled by industrial abundance, created a psychological advantage that German intelligence reports documented with growing alarm. A captured German after-action report from the Tunisia campaign, translated by American intelligence officers, stated, "American armored units display reckless disregard for equipment preservation. They operate vehicles beyond safe thermal limits, yet suffer no apparent reduction in operational readiness." Captured maintenance logs show engine replacements occurring as routine preventive measure, not emergency repair. This suggests parts supply capacity far exceeding our intelligence estimates. The report's dry language couldn't hide the fear beneath. German officers were trained to think in terms of resource management and tactical efficiency. The idea that an army could simply ignore conservation because supply was effectively infinite was alien to their operational philosophy. It violated the fundamental assumptions of how armoured warfare worked. But for American tankers in North Africa, the practice of running engines hot became so routine that it stopped being a deliberate tactic and became simply how things were done. Sergeant Kowalski, whose informal innovation had spread through the 1st Armoured Division, moved on to other practical discoveries. His crew learned they could partially disable engine governors to get slightly more horsepower at the cost of accelerated wear. They learned they could spray water on the engine deck to cool it enough for even higher sustained power output. They learned that if they broke something, supply would have a replacement before they finished the paperwork. The Sherman's maintenance schedule reflected this philosophy. Every 500 miles, or roughly every month of combat operations, the entire power plant could be pulled and replaced in about 8 hours by a crew of mechanics who didn't need specialized training. The engine, transmission, and final drives came out as a single unit, and a fresh one went in. The old unit went back to a depot for rebuilding or scrapping, depending on condition. German tanks required disassembly for major repairs, pulling individual components in sequence with special tools and skilled labour. A transmission failure on a Panzer could mean weeks of careful work. A transmission failure on a Sherman meant 8 hours with standard tools and a replacement unit that had been pre-built in a factory in Detroit. This industrial approach to warfare extended beyond engines. American tankers learned they could be careless with other components too. Tracks wore out from aggressive maneuvering through rocky terrain. New tracks arrived in crates. Final drive gears ground down from hard use. Swap the entire unit. Radios damaged from firing shock? Replace it. Don't repair it. Lieutenant Robert Hayes, a Sherman tank commander with the Combat Command B, 1st Armoured Division, participated in the final assault on Tunis in May 1943. His after-action report, preserved in the U.S. Army Heritage and Education Center, describes the operational tempo that overheating engines enabled. Advanced 40 miles in 18 hours with minimal halts, sustained combat maneuvering for 6 hours without engine shutdown, engaged enemy positions immediately upon contact with no warm-up delay, lost 2 tanks to enemy fire, 0 to mechanical failure, replaced engines on 3 tanks that night as preventive maintenance, all tanks operational for next day's mission. That final sentence contained the quiet revolution. Replaced engines on 3 tanks that night as preventive maintenance. Not because they'd failed, but because they'd been run hard enough that failure might be imminent. Why risk it when fresh engines sat in crates at the supply depot? The engines that came out probably had another 1,000 miles of life in them, but American logistics didn't care about extracting every last mile. They cared about operational readiness. The strategic implications rippled through every level of military planning. General George Patton, who would later command the Third Army in Europe, observed American tank operations in Tunisia and understood immediately what the continuous running engines represented. It wasn't just a tactical trick. It was proof of industrial supremacy so complete that his forces could afford to waste resources deliberately. Patton's diary entry from April 22, 1943 captures his thinking. The Hun still fights with skill and determination, but he fights poor. His tanks sit cold until needed, conserving every drop of fuel, ours idle hot, ready to move instantly, burning fuel we have in such abundance that waste becomes doctrine. This is how a rich nation makes war, and poverty cannot defeat it regardless of tactical skill. German commanders facing this reality struggled to adapt. They couldn't replicate the American practice because they didn't have the fuel, didn't have the parts, and didn't have tanks engineered for such abuse. Oberst Rudolf Lang, commanding a panzer regiment in Tunisia, wrote in his combat journal, "The Americans attack with material contempt we cannot match. They break their own equipment through overuse, then simply acquire new equipment. We must husband every resource, and thus we are always one step slower, always reacting rather than choosing the engagement." Part 2. The mathematics of this industrial disparity became brutally clear as the Tunisia campaign accelerated toward its conclusion. American supply officers kept meticulous records that reveal the staggering scale of resource consumption. In April 1943 alone, American armored units in Tunisia consumed over 3 million gallons of gasoline. Of this total, intelligence estimates suggested that approximately 20 to 25% was burned through extended idling, continuous engine operation during static positions, and aggressive high-temperature maneuvering that consumed fuel at rates above doctrinal standards. This wasted fuel, nearly 750,000 gallons in a single month, exceeded the total fuel allocation for all German armoured forces in North Africa during the same period. The Americans were burning more gasoline in inefficient operations than the Germans had available for all operations combined. This wasn't a marginal advantage. This was the difference between poverty and wealth made visible on the battlefield. Sergeant First Class Raymond Webb, a supply sergeant with the 1st Armoured Division, maintained personal records that now reside in the Library of Congress. His notes from late April 1943 include a remarkable observation. Not one request marked as combat, all routine preventive replacement after high-temperature operation. The boys are running these Shermans like they're stealing them, and nobody in supply even blinks. We've got engines stacked in depot like firewood. The stacked like firewood image captures the reality of American logistics. Supply depots near the front contained hundreds of complete Continental engines, still in their protective cosmoline coating, ready for installation. Each engine represented roughly 8,000 pounds of steel, aluminum, and precision components that had been manufactured in America, shipped across the Atlantic, transported across North Africa, and stored within miles of the fighting. The logistical achievement was staggering, but to American quartermasters it was simply routine. British liaison officers, attached to American units, watched this display of material abundance with complex emotions. Captain Edward Thornton, serving as a liaison between British 8th Army and American II Corps, wrote in his official reports, "Yet they achieve higher operational readiness rates than our more conservative approach. They replace components that might still function adequately, because new components are readily available. The effect on combat capability is undeniable. Thornton's report highlighted something that challenged British military culture. The British Army, fighting since 1939. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. And struggling with resource constraints from 4 years of war, had developed sophisticated maintenance procedures designed to extract maximum life from every component. British mechanics could rebuild a tank engine with minimal spare parts, improvising solutions with whatever materials were available. This skill was born of necessity, not choice. American mechanics, many of them drafted factory workers with only months of training, didn't have these improvisational skills. They didn't need them. When something broke or showed signs of wear, they replaced it with a new part from the supply system. The replacement arrived quickly, was installed using standardized procedures, and the tank returned to combat. It was less elegant than British improvisation, but more effective at maintaining operational tempo. The German experience stood in stark contrast to both Allied approaches. Hauptmann Friedrich Weber commanded a maintenance company attached to the 21st Panzer Division during the final months in Tunisia. His unit consisted of some of the most skilled mechanics in the Wehrmacht, men who could machine parts by hand, rebuild transmissions from scavenged components, and keep tanks operational through sheer technical expertise. Yet, by April 1943, Weber's skills couldn't overcome the simple mathematics of supply. His maintenance logs, captured after the German surrender and now archived at the National Archives in College Park, Maryland, tell a story of increasing desperation. April 3rd. Received no spare parts this week. Cannibalized 3 disabled tanks to keep 7 operational. April 10th. Requested bearings for Panzer IV transmission. No response from logistics. Attempted to fabricate replacement using workshop lathe. Part failed after 30 kilometers. April 17th. Fuel shortage prevents even minimum operational movement. 6 tanks mechanically functional, but cannot be deployed due to empty tanks. By late April, Weber's company, which had begun the Tunisia campaign with 24 tanks, could keep only 9 operational at any given time. The others sat immobilized, not from battle damage but from accumulated mechanical failures that couldn't be repaired without parts that would never arrive. The Mediterranean supply lines were cut. The factories in Germany couldn't produce enough parts even if they could be delivered. The mathematical reality was closing in. Meanwhile, across the valley, American maintenance companies were replacing entire engines prophylactically to avoid the possibility of failure during upcoming operations. The contrast couldn't have been more stark. The tactical advantages of hot-running engines manifested decisively during the final offensive toward Tunis and Bizerte in late April and early May 1943. American armored forces, now experienced and confident, pushed forward with an aggressive tempo that German commanders couldn't match. When American tanks encountered resistance, they attacked immediately, engines already at combat temperature, crews coordinated, weapons ready. German tanks, conserving fuel and avoiding thermal signatures, needed critical minutes to start cold engines and prepare for engagement. In armored warfare, minutes determined survival. The tank that reached effective firing position first, that maneuvered to advantageous terrain first, that brought its gun to bear first, usually won the engagement. American tankers, running their engines hot and ready, consistently achieved these advantages. Private First Class Eddie Collins, a driver in a Sherman tank with Company B, 66th Armored Regiment, 1st Armored Division, survived the Tunisia campaign and later recorded his memories for the Veterans History Project. His account describes a typical engagement near Mateur in early May. We'd been sitting in position for maybe 2 hours, engine running the whole time. Lieutenant said keep her hot in case we need to move fast. German tanks appeared on the ridge about 800 yards out. We were rolling before they got their engines started. By the time they were moving, we had the position we wanted, lower ground with better hull-down protection. Their first shots went high. Ours didn't. That engagement, multiplied across dozens of similar contacts during the final push, demonstrated how industrial superiority translated into tactical advantage. American crews could afford to waste fuel maintaining readiness. German crews couldn't, and paid for that poverty with worse positions and higher casualties. The Sherman wasn't a better tank than the Panzer Mark IV in direct comparison of armor, firepower, or mobility. But the Sherman, supported by unlimited fuel, spare parts, and replacement engines, was vastly superior to the Panzer strangled by supply shortages. The psychological impact on German tankers was devastating. Unteroffizier Klaus Becker, a gunner in the 21st Panzer Division, was captured during the final collapse in mid-May 1943. His interrogation reports, declassified in 1998, reveal the demoralization that industrial disparity created. "We knew we were outmatched when we heard their engines running all night. They have so much fuel they burn it for nothing, so many spare parts they replace working components, so many tanks that losing one means nothing. We fought well, but you cannot fight arithmetic." Becker's phrase, "you cannot fight arithmetic," became something of a recurring theme in German prisoner interrogations from Tunisia. Professional soldiers who'd fought since Poland or France, men who respected American fighting spirit and recognized improvements in American tactical skill, all returned to the same fundamental observation. The Americans could afford to be wasteful because their industrial base made waste irrelevant. Germany couldn't match that material superiority, regardless of tactical skill or ideological determination. The final statistics from the Tunisia campaign illustrated this disparity with brutal clarity. When Axis forces surrendered on May 13, 1943, over 275,000 German and Italian troops entered captivity. The armoured forces that had fought so effectively under Rommel, that had mastered desert warfare, that had defeated British armour repeatedly, ceased to exist, not primarily from battlefield losses, but from the accumulated effects of industrial strangulation. American armoured losses during the same period were significant in absolute numbers, but meaningless in strategic terms. Approximately 300 Sherman tanks were lost to enemy action during the Tunisia campaign. Every single one was replaced, often within days. By May 15th, American armoured strength in North Africa was higher than it had been in February when the final offensive began. Losses were merely opportunities to deploy newer production models with improved components. German armoured losses couldn't be replaced at all. Each panzer destroyed represented irreplaceable industrial capacity and trained crews. By the end, German units were fighting with whatever vehicles still functioned, mixing different tank models in the same units, using captured equipment because German equipment was unavailable. The organizational discipline that had made the Wehrmacht so effective deteriorated under the pressure of material deprivation. The practice of running tank engines hot, of deliberately wasting resources to maintain operational readiness, became embedded in American armored doctrine for the rest of the war. When American forces landed in Sicily in July 1943, Sherman crews idled their engines through the Mediterranean nights, burning fuel lavishly because they could. In Italy, during the grinding battles of the Gustav Line and Anzio, American tanks sat in ready positions with engines running, prepared to support infantry assaults instantly. Most significantly, when American armor landed in Normandy on June 6, 1944, this doctrine shaped tactical planning. Sherman crews knew they could push their engines harder than German crews could push theirs. They knew they could maneuver more aggressively because replacement engines and parts existed in massive supply dumps throughout England. They knew that mechanical reliability and industrial support gave them advantages that armor thickness and gun caliber couldn't overcome. General Omar Bradley, commanding First Army during the Normandy campaign, understood these advantages explicitly. His memoir, A Soldier's Story, published in 1951, includes reflection on North African lessons. We learned in Tunisia that material superiority is meaningless if you cannot project that superiority onto the battlefield continuously. The Sherman's greatest strength wasn't its gun or armor. It was that we had thousands of them, supported by parts inventories that ensured mechanical readiness, regardless of how hard we pushed them. Bradley's observation captured the essence of American military-industrial philosophy that the overheated engines represented. Victory came not from individual technical superiority, but from systematic application of overwhelming material resources. The Sherman tank, running hot through North African nights, wastefully burning fuel that Germany desperately lacked, became the symbol of this approach to warfare. German military analysts after the war, particularly those involved in rebuilding West German armed forces during the Cold War, studied American industrial military practices extensively. Former Wehrmacht officers like Franz Halder and Hermann Balk, working as advisors to the new Bundeswehr, emphasized in their reports the importance of logistics and industrial capacity over tactical elegance. The lessons learned facing American abundance in Tunisia shaped how West Germany approached military doctrine in the 1950s and 60s. One particularly telling document, now held at the German Military History Research Office in Potsdam, is a 1957 training memorandum written by a former panzer officer who'd fought in Tunisia. The memorandum, titled Industrial Warfare and the Fallacy of Tactical Perfection, argues, "In Tunisia, we learned that wars between industrial powers are won by the side that can project material superiority consistently. Our tanks were technically superior in many respects, but superiority that cannot be sustained through reliable supply becomes irrelevant. The Americans understood this. We did not." The technical legacy of the Sherman's high-temperature operations influenced post-war tank design across multiple nations. Soviet tank designers, who'd received thousands of Shermans through Lend-Lease and studied their operating characteristics, incorporated similar over-engineering of thermal tolerances into post-war designs like the T-54 and T-55. British tank development, particularly the Centurion series, emphasized reliability and ease of maintenance over pure performance specifications. Even the Germans, rebuilding their military with American support during the Cold War, adopted procurement philosophies that prioritized operational readiness rates over individual vehicle perfection. The Leopard tank program of the 1960s emphasized standardized components, high mean time between failures, and rapid maintenance procedures, all lessons learned from facing American industrial warfare in North Africa. For the tankers who actually practiced the technique of running engines hot, the experience shaped their understanding of how modern war functioned. Interviews with Sherman veterans, conducted by the U.S. Army Center of Military History in the 1980s and 90s, reveal a consistent theme. These men, many of whom went on to careers in industry and manufacturing, internalized lessons about the relationship between industrial capacity and military effectiveness. Harold Thompson, who served as a tank commander in Tunisia, Sicily, and Italy before being wounded in 1944, later worked as a production manager for Caterpillar Tractor Company. In a 1992 interview, he reflected, "In the tank, we learned you could push equipment hard if you had the supply system to back it up. That lesson applied to everything I did in civilian life. Don't baby the equipment, use it hard, maintain it properly, and have parts ready when needed. That's how you win, whether it's a war or a construction contract." Thompson's perspective, shared by thousands of veterans who translated military experience into industrial careers, helped shape post-war American manufacturing culture. The aggressive utilization of equipment, supported by robust supply chains and standardized replacement procedures, became characteristic of American industrial practice in ways that traced directly back to lessons learned in combat. The story of overheated tank engines in North Africa remains relatively unknown compared to dramatic battles or heroic actions, yet it illustrates fundamental truths about how World War II was actually won. The conflict wasn't decided primarily by superior tactics, better training, or even more advanced technology. It was decided by industrial mathematics, by the side that could produce, deploy, and maintain military equipment in quantities that made conservation irrelevant. German tankers in Tunisia, starting their engines carefully to conserve fuel they barely had, represented an army strangled by industrial limitations. American tankers, running their engines hot through desert nights, wastefully burning fuel they had in abundance, represented an army supported by industrial capacity so vast that waste became doctrine. The contrast determined the outcome as surely as any battle. When Sergeant Mike Kowalski, whose informal innovation had spread through the 1st Armored Division, finally rotated back to the United States in late 1943, he carried with him a lesson that transcended tactical minutiae. He'd learned that in modern industrial warfare, the side that could afford to be careless with resources usually defeated the side that had to be careful, regardless of tactical skill or individual courage. It was a harsh lesson, brutal in its implications, but undeniably true. The Continental R975 engines that powered the Sherman through North Africa, idling through countless desert nights, burning fuel lavishly, represented more than mechanical devices. They represented an industrial philosophy that America could project globally, while Germany could barely sustain locally. They represented the mathematics of production, defeating the elegance of engineering. They represented, ultimately, why one side won and the other lost. In the end, the practice of running tank engines hot wasn't about thermal efficiency or mechanical optimization. It was about demonstrating, to friend and enemy alike, that America possessed resources so vast that deliberate waste became acceptable. It was about psychological warfare, waged not through propaganda, but through the simple act of letting engines idle when every military tradition suggested they should be shut down. It was about teaching the Wehrmacht, through the wasteful purr of Continental engines across desert valleys, that they were fighting an enemy whose industrial strength made their own careful conservation look like poverty. The lesson resonated through every subsequent campaign of World War II. From Sicily to Normandy, from the Ardennes to the Rhine, American armor operated with the confident aggression that unlimited supply enables. Sherman tanks pushed hard, broke frequently, and were replaced immediately, maintaining operational tempo that Axis forces, struggling with supply shortages and mechanical failures, couldn't match. The overheated engines of Tunisia became the template for victory through material abundance, a lesson that German prisoners like Obergefreiter Schneider learned while watching American tanks idle through the night, burning fuel their captors possessed in quantities that made conservation meaningless. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.